This is a recording of what we will be talking about in class on Wednesday, January 12th and Thursday, January 13th. As a quick review, and this is mainly because I got to different places at the end of each class and I'm not sure who knows what, so I'm going to cover a few things really quickly. First of all, conservative forces. Some classes we talked about them and some classes we didn't. Conservative forces are forces like the gravitational force and spring forces that are associated with potential energy. If it's a conservative force, there's going to be a potential energy associated with it. When a conservative force is exerted, it will change one type of mechanical energy into another type of mechanical energy. So like if I have a ball and it's up here and it has gravitational potential energy and it falls, well, the earth is doing work, the gravitational force is doing work, and that gravitational potential energy is being changed into kinetic energy as the object falls. So from one kind of mechanical energy into another. And if I were to put a spring here, if the ball falls and it hits a spring before it hits the ground, then this gravitational potential energy, when the ball hits here and it squishes the spring down, now it was converted to kinetic energy just before it hit, and then it's converted, the spring force will be exerted, and it'll be converted to elastic potential energy. So if only conservative forces are acting, then total mechanical energy is conserved, and we defined those terms the other day. Non-conservative forces are forces like friction, any drag force, like air resistance. Air resistance is a drag force, RES. These convert mechanical energy into some other form, like thermal energy. Now, sound is another thing. Non-conservative forces might convert mechanical energy into sound, but generally it's into non-recoverable kinds of energies, like thermal energy. So the ones you need to be aware of are gravity and spring forces are conservative, and friction, any drag force like that, is non-conservative. So friction will generally take energy out of your system, or at least take any potential energy or kinetic energy away. Okay, total mechanical energy. We got three kinds of mechanical energy, and they are gravitational potential energy, which you have also seen me write UG, and elastic potential energy, which you have also seen me write as UE, and kinetic energy, which I have also written as just K. So total mechanical energy, the word total added up. So the total mechanical energy is simply equal to the gravitational potential energy plus the kinetic potential energy plus kinetic energy. And remember, this is how we calculate each one of those. When we say that total mechanical energy is conserved, we mean that this sum is constant. So conservation of energy means that throughout some process, the total mechanical energy is constant, is unchanged, does not increase, does not decrease, stays the same. Okie doke. All right, so that's our quick review. We have done LOL diagrams in class. Hopefully, if you have not been here, you've watched a video that I have put up about LOL diagrams. So we're going to work some conservation of energy problems now. And this is the whole reason we learned LOL diagrams, is because they're tools that help us to do this. A 2-kilogram block of wood is dropped from a height 3 meters above the ground, and it falls. What is the speed right before? Okay, what we mean by this is y equals 0. So it has begun to interact with the ground, but it still has that maximum velocity. It's going as fast as it goes. It has not begun to slow down with this interaction yet. So some students are like, oh, but there's still a little bit of gravitational potential. No, all the gravitational potential energy is gone. It has its maximum velocity. It just hadn't started to slow down and stop yet. All right, so let's be clear about that. Let's choose our system first. As you guys that have been in class know, what you want to do here, because you're going to look at this and you're going to, oh, there's gravitational potential energy, but not unless you put the Earth in your system. So you're going to put the block and the Earth in the system. And actually in this problem, they told us that we want the block and the block Earth system. Okay, so what energy does it have to start with? It has nothing but gravitational potential energy. So I'm going to put a few blocks of gravitational potential energy here. There is no spring energy because there's no spring or anything elastic, and there's no kinetic energy because it's not moving. So is there anything added? No, there's no. These two things are interacting. The Earth and block are acting on each other. That's why the potential energy is going to be changed, but there's no friction taking energy out. There's no energy in or out. Final energy. Well, if I've got 1, 2, 3, 4 blocks of energy over here, and there's no energy in or out, then that means I have to have 4 blocks here. Well, y equals 0, so there is no gravitational potential energy, and there's still no spring energy. And so it all has to be kinetic. So why does that help me? Now I can write my conservation of energy equation, because the point is, what is the speed of the mass right before striking the ground? And so my equation is the total mechanical energy remains unchanged. Now, mechanical energy can increase if we were to have said energy is added, or it can decrease if energy leaves. And so then our conservation of energy equation has to say, well, this is our energy at the beginning, we added, we took away, and now this is our energy at the end. But there is no energy added or taken away. So our equation is just going to be that the gravitational potential energy, I need to get in the habit of UG because it's easier to write, at the beginning, and I'm going to say initial, we'll call this is initial, is there's nothing to add, nothing to take away, so it's equal to, what do I have over here? Kinetic energy at the end. So mg delta y is equal to 1/2 mv squared. Now be careful, if the problem had said calculate one of these two types of energies, then you won't be able to do what I'm going to do now. But all I want to do is find this velocity. I see that the mass is here and the mass is here. And while they gave it to us, we don't care, because since it's on both sides of the equation, it cancels out. You can divide both sides by m and it goes away. So now if I want velocity, if I solve that equation, I get v equals the square root of, multiply both sides by 2g delta y, which is the square root of 2 times, remember, 10 meters per second squared, and the change in height, 3 meters. So 2 times 10 is 20, times 3 is 60, and the square root of 60 is 7.7. So the velocity at the very bottom is 7.7 meters per second. Okay. Next example, block of wood is thrown downwards. So there it has an initial velocity of 5 meters per second at the top, from a height of 5 meters, and the block is 4 kilograms. How fast will it be going? We're still looking for the final velocity here, just before it hits the ground at y equals 0. They show a little space here, but that's just so that you don't go, oh, well, it's not moving at all. Y equals 0. It's beginning to touch the bottom. Okay, so we're going to go through this again. What kind of energy does it have? Well, it's got, let's make our system, sorry. So we have a block, and we know now that if we're going to have gravitational potential energy, then we need to have the Earth as part of our system. So we've got gravitational potential energy, and sorry, that's squiggly. 4 blocks of gravitational potential energy. Okay, what else is going on? Up, things moving, so it's got kinetic energy. So let's say that it's got 2 blocks of kinetic energy. So 1, 2, 3, 4, 5, 6 blocks total. There's no energy in, there's no energy out. There's not going to be any friction to take energy away. So, and while there is work being done, it's work, the earth and the block are doing work on each other. And so we don't have to say energy in or out. The energy will stay within the system. So what do we have going on here? Well, there's no spring energy because there's no spring. There's no gravitational potential energy because it's at the bottom and the height is 0. So all of the energy that was over here has to be kinetic energy over here. So 6 blocks, 1, 2, 3, 4, 5, 6. So it's all the way at the top. So now when we do our conservation of energy equation, we're going to have the kinetic energy initially plus the gravitational potential energy initially, nothing added, nothing taken away, so just equals the kinetic energy final. And remember, we're looking for that final speed. I'm going to rearrange this. Gravitational potential energy initial must be equal to the final kinetic energy minus the initial kinetic energy. If I move that initial kinetic energy over here. So I get mg delta y equals 1/2 mv final squared minus 1/2 mv initial squared. I'm going to come up here and start working. Okay, again, notice I've got mass everywhere. And what does that tell me? That tells me that I can divide everything by mass and the mass goes away. Again, if you had to calculate one of these energies, you'd have to use the mass. But since that's not what we've been asked to do, we can just divide that mass out. Okay, this leaves me with g delta y. That's 10 meters per second, and the height is 5 meters. Is equal to 1/2 m vf squared. I mean, no, the m's canceled, so 1/2 v final squared. That's what we're going to end up looking for, minus 1/2 times the initial velocity. I'll have the square root of that. I told y'all in class that's the most common mistake students make. 5 meters per second on v squared. So that's 25, and half of that is 12.5. So this is 10 times 5 is 50 minus 12.5. 1/2 of 25 is 12.5. Oh, I'm sorry, plus. Because it's negative over here, we're going to add it. Equals 1/2 vf squared. Multiply both sides by 2. And so that's going to be 50, and 12.5 is 62.5 times 2 will equal v squared. I'm taking up all my space. And I'm going to take the square root of both sides, and this means the square root of, is that 125? Because 62.60 times 2 is 120, 2.5 times 2 is 5. Okay, equals v, and I'm going to put that in my calculator. 125 square root is about 11.2. Okay? Another example, this object is thrown into the air. Now, you may remember these problems, all of them that we've done so far in this presentation, we did before when we did kinematics. We just had to use acceleration and that kind of stuff. But it's actually easier to apply conservation of energy to these problems. A 10 kilogram block is thrown upward with an initial velocity of 4 meters per second. How high does it go? Okay. So let's talk about energy and what kind of energy does it have. It has kinetic energy because it's moving. And I'm going to give it 1, 2, 3, 4, 5 blocks of kinetic energy. And it has no potential energy because it's at the ground. It has no spring energy because there's no spring. I forgot to define my system. The system is going to be, again, the block. It's actually in the problem. And the earth. Okay, so how's it going to end up over here? Well, at the end, when it reaches its maximum height, it's not moving anymore. At least if it's going straight up and down. If it's thrown at an angle, it does. So it has no kinetic energy. Again, there's no spring energy, so it has to have nothing but gravitational kinetic energy. And how much? Well, it has to have the same amount of, since nothing's added, nothing's taken away, and there's no other kind of energy, 1, 2, 3, 4, 5 blocks. 1, 2, 3, 4, 5. So now I can write my equation. So initially, my energy at the beginning, this is how you write conservation of energy equations. Your energy at the beginning, and all I've got here is kinetic. So the kinetic energy initially, nothing added, nothing taken away, must be equal to the gravitational potential energy at the end. So this gives me a 1/2 m initial velocity squared equals mg delta y. One more time. Now don't just cancel these m's or divide them out. Don't just always say m's disappear, because they don't always. If you are asked to calculate the energy in between, you have to stop and calculate the energy using the mass. So it doesn't always go away. Okay, so assuming they go away and we're solving for delta y, that just means I have to divide both sides by g, right? So that gives me delta y must be equal to initial velocity squared divided by 2g. See, the 2's already in the denominator, and then I divide both sides by g. So that's initial 4 squared divided by 2 times 10. That's 20. 4 squared is 16 divided by 20, and 16 divided by 20, I think, is 0.8. 16 divided by 20, 0.8 meters. Okay? Now, these diagrams are really fast to draw, and they build our equation for us. So you're not scrambling around going, what equation do I use? How do I know? You build it. You do your diagram, you think of what the energies are at the beginning and the end, build your diagram, the equation comes straight from that, and you've got it. Okay, now we're going to do one I told you just a second ago, objects at an angle. These were very complicated to do. Remember, we had to use sine and cosine, and they're simpler now. So let's see, we have a 4 kilogram block of wood thrown. Okay, so the initial speed is 10 meters per second. It reaches a maximum height of 3.75 meters. And the question is, what is the speed of the block when it has reached this maximum height of 3.75 meters? How fast is it going? Okay, let's get this energy diagram done quickly. What kind of energy does it have at the beginning? It's on the ground. So it has no potential energy. It has no spring energy. It only has gravitational kinetic energy. Let's give it some of that. Oh, forgot my system again. My system is the block and the earth. Okay. So what kind of energy do I have when it's on this side? Well, obviously there's no spring energy, so we can cross that out. It is still moving. Now in the previous example, it was not still moving at the top because it was thrown straight up into the air and all the vertical velocity is gone. Well, all the vertical velocity is gone here too, but there's still horizontal velocity, so we need to find that. So now it's got two kinds of energy. You see that? It's got height, so it has to have some gravitational potential energy, and it's still moving, so it has kinetic energy. These blocks plus anything added minus anything taken away equal these blocks. So 1, 2, 3, 4, 5, nothing added, nothing taken away. 1, 2, 3, 4, 5. And now we can write our equation using our diagram. So kinetic energy initially is equal to kinetic energy final plus gravitational potential energy final. So I have a 1/2 mv squared, the initial squared, equals 1/2 mv final squared plus mg delta y. What am I looking for? I'm looking for that value right there. Now I'm going to do this the right way. I kind of sub values in too early. Before I am going to go ahead and take that mass out because I can. I'm going to say that mass, that mass, that mass, all divide. I can divide all three terms by that, and so it goes away. So I'm going to move this term over here, and I'm going to have a 1/2 initial velocity squared minus g delta y equals 1/2 vf squared. I want to solve for vf squared, so I have vf equals the square root of, I'm going to multiply the other side by 2. So when I say 2 times, let me do this in a different color real quick. If I multiply this side by 2, that means I'm going to have 2 times 1/2 makes 1. So I'll just have initial velocity squared, but then when I distribute it, it has to stay over here, minus 2g delta y. And I'll plug stuff in, and I get vi squared, what was it, 10 squared minus 2 times 10. This is the g, 10 times the delta y, and the height was 3.75 meters. This out. Use my calculator. 2 times 10 times 3.75. That gives me 75. And you know this is 100. Well, that's going to be the square root of 25 then, right? 100 minus 75. And we can do that in our heads. That's 5 meters per second for the final velocity. I'm going to do one more of these, and then we're going to start doing a little bit of positive physics. A 20 kilogram block starts at rest against a spring constant K equals 300 newtons per meter. It's compressed. Okay, so it has been compressed by a distance of 2 meters to get it here. So work was done compressing that spring. There is friction, and the kinetic friction, this is the most complicated problem we've done and will do, is 0.5 between the ground and the block. What speed will the block have when it leaves the spring? So this sounds like a very overwhelming question. It's not. We can do this. What is our system? Okay, I'm going to say the block. The spring. I don't need to put the earth in because I'm not going to have any gravitational potential energy because it doesn't go up and down. You can if you want to. Doesn't hurt. I am going to put the surface. And I'm going to put the surface because because if I don't put the surface, then I'm going to have to lose energy. You know, I'm going to have to do one of these arrows to show that the friction, it's a non-conservative force. It's going to take energy out of my system, but not if I put the floor in my system. Okay, so let's talk about energy types. We got, what do we got? Spring energy for the first time. Let's have a lot of that because that's all we got, isn't it? Let's just take it all the way up. 1, 2, 3, 6 blocks. There is no gravitational potential and no kinetic because it's not moving. Nothing in, nothing out. Again, if we didn't put our surface in here, as the box slides over this 2 meter distance, it would lose some energy, and we would have to do an arrow out. But since they're in there, we're just going to be able to say thermal energy over here. So let's do our right-hand side. It is moving, it has kinetic energy, so there's just going to be stuff here, and there's going to be thermal energy because as the block rubs against the floor, as they rub against each other, the thermal energy is going to be created by the work done by friction. And there's no gravitational potential or spring energy anymore. Okay, so now we set up our equation. We have spring energy, nothing in, nothing out, must be equal to kinetic energy. I'm going to do an initial here and a final here, plus, and now I don't have an equation for thermal energy, but that thermal energy is the work done by friction. the friction will take energy away by doing work on the system, do negative work. Remember, we talked about this. So, so I'm going to put a minus there since it's going to, no, plus the work done by friction. And how do we calculate the work done by friction? Remember, work is force times distance, and the frictional force is the normal force, coefficient of friction times the normal force, and the normal force is going to be mg. So the frictional force is going to be 0.5 mu times normal force, which is mg, and the mass is 20 kilograms, and gravitational acceleration is 10 meters per second squared. So 1/2 times 20 is 10, times 10 is 100. So 100 newtons is my force. And so the work done by friction is force times distance, 100 newtons times, where this happens right when they leave, and so the distance it's going to push it is this 2 meters that it was compressed to set the problem up, times 2 meters. So the work done by friction is going to be 200 joules. Okay, so that's this bit. So I didn't draw, I don't even know what the kinetic energy is, so I don't know how big to draw them. So I'm going to draw that up to 4, and I'm going to draw this up to 2. And you don't have to readjust it if you find the numbers don't work. It's just a model. Okay, so spring energy is 1/2 kx squared, and kinetic energy is 1/2 mv squared, and I've already found my work done, 200 joules. So what am I looking for here again? Well, oh, the velocity, looking for that. So I want to get that by itself. So I'm going to move this to that side. So I'm going to have 1/2 kx squared minus 200 equals 1/2 mv squared. And I'm going to go ahead and start plugging numbers in. 1/2 k was 300. The distance was 2 meters. 1/2, and our mass was 20 kilograms, and we don't know that. So 2 squared is 4, and 4 times 300 is 1200, and half of that is 600 minus 200 equals half of 20, so 10v squared. So divide both sides. This is 400. Divide both sides by 10, and I get 40 equals v squared, and v must be, use my calculator, 6.3. Okay, the most complicated problem we're due. See, it's quite doable. And even if you look at it at the beginning and you're like, I have no idea what to do, just follow the steps. Do your diagrams. You know how to calculate this stuff. This is from this unit. This is from a previous unit. You can do that. Okay, so now we're going to use some positive physics. I'm going through this quickly. This video is getting long. All right, let's do some positive physics. Okay, so he's sitting here. He's not moving. There is no energy. So the total energy here is 0. He's going to go up this hill and he's going to pedal. So he's going to do work in the amount of 530 joules. While he's doing this, air resistance and friction in the tires and all that stuff is going to take 60 joules of energy away. So this is energy added. This is energy taken away. Okay? So now, how much gravitational potential energy does he have? Well, if he did 530 joules of work but lost 60 joules, and I subtract 60 from 530, 530 would be 470. So the total energy here is 470. There was no energy. Work was done by a non-conservative force. Energy was increased. if out of that 470, 370 is gravitational potential, then 100 must be kinetic energy. 100 plus 370 is 470. Okay, so now he's going to coast down the hill. So no more work, and gravity's acting, that conservative force, but there's also a loss due to friction kind of things of 150. And so the total energy will go down. Pardon me. If it lost 100, it would be down to 370, so 320. It has no more gravitational potential energy, so the remaining kinetic energy must be 320 joules. There's no energy. Work is done. He's going to stretch that stretchy stuff back and do work, 320 joules. Total energy is 320. The spring energy or elastic potential energy that is now stored in those rubber bands is 340 joules. There's no work or loss when he lets it go. That's what happens between here and here is he's let it go. And so I must have written this after I did show answers because there's nothing for you to fill in. Just no work or loss, and that means the total energy stays the same. And since the only kind of energy that's there is kinetic, you've got 340 joules of kinetic energy. So sorry, not much to go on there because it was hard to build it. Okay, this is our last problem, and I'll try to go through it quickly. This is from Complete Problems 2, I think. So I wanted to use one that was a little bit more complicated. A student fires a 50-kilogram cannonball as shown. The cannon exerts an average force of 540,000 newtons while the cannon goes from here to here, like during this distance. And that distance is 0.66 meters. I like to write the numbers down where I can see them. Neglect the initial height of the ball. So that means the reference level is here. So we don't have to worry about this height. And pretend there's no air resistance or anything. List the energy types at the initial and final time and whether or not work was done, work done or lost due to non-conservative forces, as well as the corresponding amounts. Okay, initially. So initially, it is sitting here and it's not doing anything. And so there is no energy. Work is done as the cannon exerts a force on the cannonball, and that work is equal to force times distance, and they gave us both of those. So I'm going to add those, multiply those two things together. 540,000, the right number of zeros, times 0.66. I get 356,400 joules. So that's the work done here, is 356,400 joules. And I'm not sure what was in these drop downs. List the energy types. Okay, so work done. So that would just be work. And there is no loss because it told us to ignore, neglect any loss in the process, so there would be no loss. And so if in this process between here and here, work was done, then, well, let's see. It's got gravitational potential energy here. Yeah, it doesn't matter how much gravitational potential energy it gained. Oh, it says neglect the initial height. So we pretend that all of this kind of happened sort of instantaneously, I guess. If I look back at positive physics and find out I'm wrong, I'm going to be embarrassed, but hopefully I won't. I was going to open it up on my other screen, but I'm not going to take the time. So let's say that it's got what at the beginning? It's got nothing. It's got no kinetic energy, but there's work done. And I'm going to say that let's 1, 2, 3, 4, 5, 6 units, and this is going to be my arrowhead. So 6 units of work. The cannon on the ball. So the ball and the earth our mass system. So what kind of energy does it have at the end? Well, it's at the maximum height. And so it's not going to have any kinetic energy. It's not going to have spring energy, thermal energy. It's just going to have gravitational potential energy. So if I did 6 units of work, that will result in 6 units of gravitational potential energy. So how do I find the ball's maximum height? The final energy should, as you can see in our diagram, should be equal to the work done. So the final energy is going to be 356,400 joules, and it will be gravitational potential energy. And so our equation is energy at the beginning, which is 0, plus anything added. Okay, so there's work done, minus anything taken away. We don't have anything taken away, equals the final energy. So equals gravitational potential energy. So we have the amount of work, 356,400 equals mg delta y equals the mass of the ball, 50 kilograms, times gravitational acceleration. So that's 500 delta y. So I'm going to divide both sides by 500. Divided by 500, and I get 712.8 meters. So I multiplied these two, divided both delta. I'm cleaning it up to make it look nice. So divide both sides by 500. 500 cancels here. There. There, that one's nice. Okay, so the most complicated problem we've done from positive physics. Again, it's from complete problems too. So until you get there, they'll be a little bit simpler. Do I have anything else? I don't think so. I think the next problem goes into, nope, don't have anything else. All right, so if you were absent, that should get you caught up. Thank you.